So I wanted to go over the mole balance for a semi-batch reactor. So first of all, there are two types of semi-batch reactors. So semi-batch reactor. And the first type is where you have, so say you have A plus B to C plus D. So for the first type, you would have either reactant A or B in your reactor already, and then you would slowly add the second one. So basically you have, here's your reactor, so let's say it has A in it. So then you would be adding B, so you would have some FB naught, V naught, CA naught. And so this is the first type, so add one reactant slowly added. So then the second type of semi-batch reactor is called reactive distillation. So reactive distillation. And what this is either C or D, one of your products, is being removed, it's either being vaporized or withdrawn continuously. So basically it's being distilled out. So then you would have A and B, and let's just say that you're withdrawing either C or D. And so for this first one, the reason why you would want to do something like this, like have one in there and then add the other slowly, is if you say you have high concentrations of unwanted side reactions, or if this is highly exothermic, you don't want to just dump everything in. Or if one of your reactants is a gas, then you can slowly bubble it, or you can continuously bubble it through the liquid. And for the reactive distillation, you would want to do this if you had a problem with low conversion because of, say, your reaction is highly to the left. So if you continuously withdraw one of the products, then you keep pushing the reaction to the right. So then this increases your final product. So let's go ahead and just do a quick mole balance on semi-batch reactor. And this is pretty much the same process as every other mole balance I've gone through. So first of all, let's say that we have A plus B to C. And then going off of this drawing, so I'll just take the D off this for now because this is the reaction we're looking at, and I just want to use this drawing. So we're going to have A is already in here, and then we're adding B. So for the mole balance on A, we just do the exact same thing we've been doing. So we have rate in minus rate out plus a generation term equals whatever's accumulating in the reactor. So for A, we know that we don't have anything in or out, so these are both 0. And then for the generation, we have RAV, so the rate multiplied by the volume. And this is equal to the change in moles of A in the reactor with time. And then we know that Na is equal to CAV. Oh, this is actually V, like that. So then we can say, we can plug this into there. So if we do that, we get d CAV dt, and this is equal to V d CA dt plus CA dV dt. So the volume varies with time, which is what we would expect with this reactor. So because the volume varies with time, we need to find an expression for this. And so to do that, we want to do a mole balance on the, we want to do an overall mass balance. So overall mass balance. And so this will be the reactor volume at any time t. So then we just do the exact same thing. So we have a rate in minus rate out plus a generation term equals accumulation. And so for this, we know that the rate in is rho naught V naught, because remember we're doing a overall mass balance. The rate out is 0. The generation term is 0. And then this would be equal to d rho V dt. And then if we assume that the density is constant, so if we say rho naught equals rho, so constant density, then we can say that we can divide out the rho naught, because if rho is constant, then we can pull it out of this derivative. So then we get dV dt equals V naught. So then we can plug this into here. And if we do that, then we get, let's see, yeah, so then we get RAV is equal to V d CA dt plus CA dV dt. Only we're plugging this in for dV dt, so this is actually CA V naught. So then we can subtract this over, and if we do that, then we get V dCA dt is equal to RA V minus C A V naught. And then we can divide through this volume. So if we do that, we get d CA dt is equal to RA minus V naught over V CA. So then this is the mole balance on A for a semi-batch reactor. So I'm going to erase some stuff real quick so I can do the mole balance on B. So I'm going to start out the exact same way, just doing the balance. So I have in minus out plus generation equals whatever's accumulating in the reactor. So for B, we know that coming in, we have F B naught. We don't have anything going out, so that's 0, plus the generation is the rate multiplied by the volume, and then this is equal to d, and the change in the moles of B with time. So then we can just kind of combine these terms, so we get d and b dt is equal to, oh, this is, sorry, this is RB, not RA. So RBV plus FB naught. And so then we can do the same thing here as we did on the other one. We know that NB is equal to CB multiplied by the volume. So then if we plug that in, then we get D CBV over dt, and that is equal to CB dV dt plus V dCB dt. So then we get RBV plus FB naught, whoops, is equal to CB dV dt plus V dCB dt. And then we also know that this is C A naught multiplied by V. Well, multiplied by V naught. And so then if you remember the overall mass balance we did on the mole balance for A, what we got was this dV over dt equals V naught. And this is the same for B as it is for A because it's an overall mass balance. So then we can just plug that in. So this is basically the same method as A, except now we're doing B. So if we plug this in for the CA naught, V naught for FB naught, and V naught for dB dt, then we get RBV plus CA naught, V naught equals V naught multiplied by CB plus V dCB dt. Oh, and I don't know what, this is CB naught, I accidentally wrote CA naught. So then just putting the derivative on one side and everything else on the other side, we get V dCB dt is equal to R BV plus C B naught V naught minus V naught CB. And then if we can pull the V naught out, so then this would be V naught CB naught minus CB. And then we can also divide through the volume. So if we do that, we get D CB dt is equal to RB plus V naught over V multiplied by, whoops, multiplied by C B naught minus CB. So then this is the mole balance on B for a semi-batch reactor. And in the book, so these are your two mole balances for a semi-batch reactor. So in the book, it also goes over a balance for a semi-batch reactor in terms of conversion. And I'm not going to go over that because it's kind of messy, but you should definitely look at that in the book.